Hello, everyone, and thank you very much, Sean, for the invitation. My name is Iris Zhang from Cook Induction. I'm a little bit nervous, sorry. It is an honor to join this discussion on zero carbon or electric kitchens. Mm, Food service operators worldwide must reduce energy use and emissions while improving safety and performance. Gas-based kitchens makes this difficult because of combustion, heat release, and ventilation are closely connected. Today, I will explain why the transition is difficult, why commercial induction can become the core cooking technology, what China has deployed at scale, and how ventilation, heat recovery, and smart management complete the system. My main message is simple. The kitchen is no longer an isolated group of appliances. It is becoming part of the building energy system. Let's begin with the challenge. Can you move to slide 2, please? Yes. Commercial kitchens are difficult to electrify for 3 reasons. First, high peak load. They have high peak load. Chefs need fast response, large capacity, and reliable recovery during busy service. Second, equipment often operate for long hours and under demanding conditions. Third, the kitchen is connected to the whole building through exhaust, makeup air, and cooling. So replacing gas equipment one for one is not enough. The electrical infrastructure, equipment line, and ventilation strategy have to be designed together. This explains why the kitchen is difficult. So it also tells us what the solution must do: deliver chef-level performance, removing on-site combustion, and reduce the heat and ventilation burden at the same time. This leads to the role of induction. Next slide, please. The challenge on the previous slide gives us 3 design requirements. We must serve performance, we must remove on-site combustion from the cooking process, and we must reduce the heat at the building has to capture, exhaust, and cool. Commercial induction is a strong answer because it delivers heat directly to the cookware, but induction alone is not the whole solution. It becomes the anchor of all electric equipment line, which must then be integrated with ventilation, heat recovery, and controls. So I will now move from the requirement to the first building block: how direct induction heating changes energy transfer and the kitchen heat balance. Before comparing gas and induction, we need to define exactly what percentage means. The most useful common commercial method is this one, ASTM, this method. It measures how much the appliance input energy is absorbed by a specified water load during the control heat up from 20 degree to 93 degree. Under this method, Energy Star requires every hoop of certified commercial electric cooktop to reach at least 80% cooking or boiling efficiency. Frontier Energy published results for 8 commercial induction hoops from 1.4 to 5 kilowatts. Their measured boil efficiencies range from 82 to 90.4%. The same Frontier report cites 25 to 45 to 40% of the natural gas open burners had tested. We should treat that as a laboratory range for those tested open burners, not a universal ceiling for every modern gas appliance. High performance burners, optimized vessels, and different test protocols protocols can produce different results. We also hear induction figures as high as 97%, but it is for some specific particular products or test boundary. So this point conclusion is not one headline percentage. It is that commercial induction consistently performs strongly in standardized boil testing, where project decisions should use test data that match the actual appliance and cooking process. With that distinction published, the next question is whether induction can operate as part of an entire commercial kitchen. China's installed project provides that evidence. Slide 5, yes, thank you. The strongest proof is the scale of kitchen already operating. Across China, all electric kitchens serve hotels, universities, hospitals, canteens, restaurants, and central kitchens. This picture shows complete cook line, high-power workstations, ventilation canopies, and conveyor dishwashers. A true all-electric kitchen includes washing, hot water, and sanitation, not only cooking. Ventilation remains essential. Removing gas eliminates combustion products, but food still produces grease, vapor, smoke, and moisture. The system must therefore be redesigned around the electric equipment and its actual cooking load. Today, commercial induction technology is no longer limited to small countertop equipment. It is now widely used in large commercial kitchens. Electric kitchens can also replace high-powered traditional cooking methods. Wok cooking is one important example. Next slide, please. Wok station, as mentioned, the interesting example is the wok cooking, which is an important part of Chinese commercial kitchens. Electric kitchen does not mean only a small countertop. The wok size. Induction technology has developed to support different wok sizes and cooking scales, from smaller woks around 300 to 400 millimeters used in open kitchens and restaurants, to larger woks to medium wok from 450 to 600 millimeters to even 700 to 900 millimeters. We actually have 1,200 millimeters wok used in high volume commercial kitchens and central kitchens.
For people who are in America, we only have inches. And so I did the conversion. 900 millimeters is about 35 inches wide. And I think that'd be about 40 inches when you got to 1,000. So continue on. I just want people to realize like they're big.
Yes. 1,200 millimeters is like a small bed. As big as a small bed. Yes, very big. This demonstrates that electric cooking is not limited to light-duty applications. It also supports all the traditional high-power cooking methods in commercial scale. Different cooking scales can be electrified. Next, please. One induction heating principle can support many cooking processes. It can be matched with a wok, stovetop, noodle tank, flat plate, tilting pan or mixing vessel, electric steamers, and combi ovens complete the line. The right question is not which cooker should we buy, it is what menu, capacity, process must this kitchen deliver. We design backward from the food, vessel, power profile, and workflow. This is how individual appliances become a complete kitchen, electric kitchen. We design this complete platform is now evolving in 4 directions: power, coverage, digital management, and engineering durability. We will move to the next generation is more powerful, complete, and measurable. The next slide.
Sorry, I'm jumping the gun there. Continue
Yes,
on.
from this installed base, we see four development directions. Thus, high power integration in our current portfolio and project work. Individual commercial induction system commonly spans roughly to 3.5 kilowatts to 30 kilowatts can be combined into multi-zone cooking suite. This is a description of our product range, not a global market statistic. Second, full kitchen coverage. The goal is not one cooker, but a coordinated kitchen line including wok cooking, steaming, stock pot, noodle system, automatic cooking and washing. Third, digital low carbon control. Equipment can report energy use, operating status, and faults, helping operators manage consumption and document improvement. Fourth, engineering integration, better power electronics, cooling system, material and compact construction improve durability and allowed adaptation to different voltage and cooking traditions. However, more equipment and more powerful do not automatically create a low carbon building. We still have to manage the largest system around the cooking line, the ventilation. We'll move to the next slide, reduce the load first, recover heat second. Heat recovery is exciting, but the sequence matters. First, induction reduces unnecessary heat release at the source. Second, the hood and appliances layout should be optimized for capture and containment with the lowest practical airflow. Third, demand-controlled kitchen ventilation can modulate fan speed according to cooking activity instead of running at full speed all day. Only after these steps should we evaluate heat recovery in many projects. Reducing exhaust and makeup air load creates a more reliable return than adding complete recovery device to an efficient system. In other words, the cheapest recovered kilowatt is often the one we avoid exhausting. After reduction and control, we can ask for a more precise question, which remaining heat steam is clean enough, steady enough, and valuable enough to recover. Um, can you give me a second? I need to leave for
It's just
for.
fine.
I sorry, a second.
It's okay. This is one of the pleasures of having a home office. I've gotten to like know Iris while she had a baby recently, like maybe it was like a year ago or something, but we've like exchanged little gifts and things, and she posted a picture from the hospital bed, and it was adorable. And so I'm assuming that is a little bit of parenting going on at the moment.
I'm sorry. It's
Not at
too
all.
early. I still at home. My kids just woke up.
It's just fine. It's just telling them that what's going on. That it's one
Yeah.
of the nicest things about the new world that we're in is that we can do these kinds of things at home. Go ahead.
Yes. Thank you. Then we continue. We'll move to the next slide. Choose the cleanest, most useful heat. Useful heat steam. Heat recovery is a portfolio of options. Exhaust air can potentially reheat makeup air or water, but Asham warns that grease can fool heat exchangers, so cleaning assets, maintenance, and fire safe and engineering are essential. Dishwashing and hot water processes may offer a cleaning source for incoming water reheat. Water waste recovery, sometimes combined with a heat pump, may suit hotels, canteens, or central kitchens with steady warm water discharge. Screening and maintenance access, must be designed from the start. The answer is project specific. We should measure temperature, flow rate, operating hours, and the real demand for recovered heat. Those measurements also lead naturally to digital management. We need data to operate and verify the system. We can move to the next slide. The need for measurement becomes clearer in real kitchen retrofit. This project was designed around an operating sequence, not around buying technology. Phase one protects food quality. This project was designed around an operating sequence, not around buying technology. Phase one protects food quality. The proposal makes critical temperature and action traceable across noodle cooking, holding, refrigeration, dishwashing, and soup preparation. Phase two addresses energy. Metering and stage control are added for lighting, air conditioning, exhaust, makeup air, and sanitation system. Phase two Phase three connects the data to management report, alarms, and selected quality control analytics. The important lesson is the order. First, make the process visible, then automate stable rules, and only then add advanced uh, analytics. The project also recommends starting with one representative pilot store before scaling. The next slide shows how equipment and IoT platform support this sequence. This is a real case we are working on. This slide brings this case architecture and the current IoT capability together. At the equipment level, connected induction system can report status, operating data, and fault information. Energy chains can be reviewed by device, while selected recipe parameters can be distributed to improve consistency across stores. At the process level, the pilot design uses sensors and cameras to make important cooking actions and temperature conditions traceable. This is not a claim that AI should replace the chef. It is a way to create evidence for training, quality review, and exception handling. At the management level, the system can support three practical actions: monitor performance, standardize repeatable processes, and respond faster to faults or abnormal conditions. Two safeguards are essential. Local safety logic and manual control must remain available, and automation should be introduced but only after the baseline process has been verified. This case turns the ideal of a smart kitchen into an implementation method. It also shows how kitchen data can connect to the wider building energy system. We can see everything, all the equipment from the back office, from the mobile or computer, to see the location, to see all the equipment status in the office. Can you move to the next slide, please? This is the future system view. A building energy management system can connect grid conditions, renewable power, electric cooking, and ventilation. Cooking schedules help manage peaks, while ventilation responds to real activity. Where a useful heat source and demand overlap, recovered energy can support hot water, makeup air, or storage. Not every kitchen needs all the technology shown here. The design target is what matters. Low peaks, low airflow, measurable energy, and useful destination for recovered heat. This resolves our opening challenge. High performance cooking can be electrified. The greatest value appears when equipment, ventilation, heat, and data are designed together. We will move to the next. Yes. That brings us back to the three conclusions I would like you to remember. First, commercial induction is a practical core technology for moving away from on-site combustion. Second, China proved commercial electrification at scale, but successfully projects are not simple equipment substitutions. Cooking, washing, electrical capacity, and ventilation must be designed together. Third, the Zhang kitchen case gives us a practical implementation sequence. Pilot one store, make the process measurable, automate stable rules, verify performance, and then depict. Smart management and heat recovery add value in the same disciplined way. Reduce waste, control airflow, measurable performance, and recover heat only where the source demand and maintenance plan fit. The future kitchen is electric and integrated. We look forward to working with global partners to build safer, cleaner, more efficient all-electric kitchens. Thank you, and I welcome your ideas.
Woo! Good job, Iris. And you
Thank
even
you.
and you did it
Um,
in English too. My gosh, you're amazing.
Thank you. I'm very nervous. I'm at home. Sometimes my kids.
Everyone, all of us were nervous. I don't think there's a single person who presented today, myself included, who didn't feel nervous. So thank you for the hard work. Um,
I hope my information is useful.
Yeah. No, I think that a lot of people they haven't thought about this before. But for everyone else to remember, the most energy dense building is a kitchen, like a commercial kitchen. If you're looking at the amount of
Yes,
energy per square foot, it's restaurants. And that's where the gas is being burned at large amounts compared to any other building that we can engage. It's restaurants where we could shut down a lot of gas. And I appreciate what you're showing us is like, this is how you do it.
yes,
And
it's an easy process because, as I mentioned, the difficulty to replace is not simply the cookers. It includes the ventilation system and um, the heat recovery,
yeah,
the many factors. So we are still working on it.
you're still working on it. Your team there is still finding ways to integrate and improve.
Yes, we have a few projects ongoing on um, the case on the slide. I think let me see. On slide 11, it is the case we are working on. It is a noodle. Yes, this one. It is a noodle restaurant. We are making this from. They will be using automatic noodle cookers, so this will automate the cooking process too. And then we will have the back office to manage their recipes, uh, monitor on their all the equipment, including the noodle cookers, the ventilation, and the dishwasher on one back office.
Can you program your machines for certain recipes?
Yes,
That's a
yes,
big
on
deal. Yeah, gas stoves are not easy to program the way that you can with an electric stove.
yes, yeah. We are also making this equipment to Europe market. We are working with a noodle restaurant brand in France on this process.